thing is called momentum integral estimate. We'll do an integral analysis on the boundary layer, get some, insight into it. We'll do a little bit of differential analysis and get a little insight into it. So let's first do the integral version. My solid plate, my boundary layer, x, y, delta, the boundary layer thickness, the uniform velocity, u infinity. I am going to consider a streamline that is going to reach this point. Okay, so that's going to reach this point. Okay, let's say that is a streamline. So what do I write? A streamline. What is a streamline? If I draw tangents to the streamline, I will get velocity vector. Can there be a flow across a streamline? No, there won't be a flow across a streamline because by definition the tangent is the direction in which velocity is. So there can't be a flow across the streamline. So let's say this height is h. The height on the right hand side is delta. And let's say d is the width of the plate. Width of the plate in z direction. Okay. So I'm looking at xy plane. Z direction is the plane or line perpendicular to the screen that you are looking at. So b is called b. Let's say is the width in that particular direction, which let's imagine to be very large. And I want to write down force balance, okay, to this control volume, which is this, that so that's the control volume that I have. So on the left hand side, it's bounded by the uniform velocity profile, okay, up to height of h. On the right hand side, the height is delta, the boundary layer thickness. On top, it's bounded by a streamline. On the bottom, it's the plate. That's the volume that I'm going to look at, and I'm going to write down a force balance. The control volume is clear? So what do we write? Momentum flux in minus out is equal to total forces. The only force, so we are writing it down on the fluid. Okay, so the solid is going to exert some retarding forces, some drag force on the fluid that's flowing, right? So let me call that force as D. So what is D? Total drag force exerted by the solid plate on the fluid in the control volume. Okay, and that should be equal to the flux in minus flux out. Yeah, you have some flux in, or the flux in is where is the flux happen. So there is only two places where the fluid is coming and leaving, right? The fluid is coming from the left hand side through a height of h. The fluid is leaving through the height delta. Since I have chosen a streamline, there is no fluid flow across the streamline. So there is no fluid flow through the top part. Okay, bottom part anyway, it's a solid plate, so there is no fluid flow through the plate. So I have to only worry about the fluid that is entering through h and the fluid that is leaving through delta. Okay, so the fluid, what will be the momentum of the fluid that's entering through left hand side H? We will say that so B into H is the cross sectional area times U infinity is the flow rate times rho is going to be my mass flow rate times U infinity is going to be my momentum flow rate. So that's going to be in the plus x direction minus what is exiting will be, if I do the same thing except that, so here on the left hand side the flow is uniform, but on the right hand side the flow is not, right? There is a profile. So I can't do just like that, I need to write down an integral. Okay, so if I take a small section, I'll say, let's say B D Y is my cross section times, let's call U as the velocity, so that's my volumetric flow rate, times rho is my mass flow rate times U is my momentum flux, integrated from 0 to delta would be the flow rate or the momentum flux out. Okay, so that's going to be in minus out is equal to the total force exerted or experienced by the control volume fluid. That's okay. Just write it neatly. D is equal to rho B H U infinity square minus integral 0 to delta rho B U square dy. Let's also write down a mass conservation principle. Fluid in is equal to fluid out. So what is the fluid in? Rho B H U infinity should be equal to integral of rho B Y U dy. Sorry, rho B dy times U. So, that's correct. So remember, this is my force balance. This is my conservation of mass. Any doubts on the equations? Total drag force is not 0. Why is the total drag force 0? That is what we have called as D. So this is D, okay, D, it's not 0. I'll try to write it better. Maybe. Okay. Yeah, I mean, our interest is to calculate really that force and connect it with the thickness. Okay, so mass conservation, if you simplify, what do you get? H. So rho goes, BB goes, H is equal to 1 by U infinity integral U dy. Okay, take that and substitute into your force balance. D is equal to rho B U infinity square. Instead of H, I'll write 1 by U infinity integral U dy minus integral 0 to delta rho B U square dy. Get one of them. So that's equal to rho B. So this limit is also 0 to delta, right? So rho B integral 0 to delta U infinity U dy minus rho B integral 0 to delta U square dy is equal to rho B U infinity square into integral, no, let me do it. Yeah, that's fine. I think u infinity square u by u infinity minus u square by u infinity square dy 0 to delta. Is this right? Okay, so that is really the drag force. Yeah, I think that's fine. Now, what we are going to do is that we are going to give this part, okay, a name, and that is momentum thickness theta. Okay, it's really a measure of drag force. Okay, so if you really look at it, d divided by rho b u infinity square is equal to theta, because that integral is theta. Okay, so that's nothing but just a measure of total drag exerted by the plate on the fluid. Now, so this is how we have gotten an expression for the drag force on the fluid, but you also know it can be evaluated from your shear stress. Okay, in other words, you know that D is nothing but tau W. If let's say tau W is the wall shear stress exerted on a small element dx, and B integrated. So, the drag force, the total drag force should be an integral of the wall shear stress, right? The force exerted by the plate on the fluid, okay, is through the viscous stresses. So, that is nothing but what you call as the shear stress. So, that I have just integrated. So, why have I done the integration? Because it need not be a constant, okay. As we saw earlier, so if you look at, you know, the first, second, third and so on, the fluid slope is going to be different, okay. So the shear stress is going to be a function of x. Shear stress will not be a constant along x. So I said, okay, if I take a small area, okay, of length dx and width b, so it's a b dx, and then on that tau w is acting. So tau w dx is going to be the force on that small element, and if I integrate it over all my length up to x, I will get the total force. Okay. So that means if I do a d by dx, I am going to get b times tau w. Okay. Or in other words, shear stress is nothing but the derivative of the total drag force with respect to x. I could also write dd by dx is equal to rho b u infinity square d theta by dx, right, where I had defined a theta as some integral, and therefore if I use these two, what I see, rho b u infinity square d theta by dx is really b times tau w, or tau w is equal to rho u infinity square d theta by dx. Okay, so it's really rewriting the wall shear stress in terms of some derivative. It's just for manipulation. All right. Now, so far we have not assumed anything about the flow profile inside the boundary layer. Okay. So, we have done an integral estimate. So, this should be true whether the flow is laminar or turbulent. Okay, so this should be true whether the flow is laminar or turbulent. Yeah. Steady state, yeah. Well, what is steady state? Yes, it is in terms of the incoming fluid, it is a steady thing, yes. Yes, but turbulent flow, you have to be careful. You must be talking about an averaged quantity, huh? Why should it be a straight line? No, in fact, the path of the particle will basically go a little up. So, okay, I can't think about any other explanation that why would it go up. But the fact is that, oh yeah, one thing is this, continuity would say that. Okay, so if you look at continuity, dou u by dou x plus dou v by dou y is equal to 0. We know that dou u by dou x is not 0. Okay, so that means that dou v by dou y is not 0. Okay, so that means v can be a function of y. Okay, so the v basically will be a function of y. That means that at every point the fluid will not only have an x velocity, it will also have a y velocity, and if it does not have that y velocity, it will have to violate the continuity equation. Or in other words, it's basically a consequence of mass conservation. What is that? No, we know that this dou u by this mass conservation is true whichever you do, right? Whether it is laminar, turbulent, whether you talk about average fluctuations and so on. So it will be true in general. Okay, so the v velocity develops because it's because the mass has to be conserved. So it must have a better explanation in terms of the total flow rate, but I can't think of anything as such. Okay, so in fact that's what we had used whenever we talked about our fully developed flow. When we talked about a fully developed flow, we said our dou u by dou x is 0 and therefore dou v by dou y is equal to 0. Okay, and therefore v is 0 at some place and v will be 0 everywhere. So, okay, so we have gotten an integral form. Now, what we are going to do is that we are going to assume that the velocity profile in the boundary layer is quadratic. Now, if you ask why it is, there is no a priori reason, but what one would see is that it basically going to serve well. Okay, so if you assume that the velocity profile inside the boundary layer is quadratic. In other words, you would assume that u is given by u infinity times two y by delta minus y square by delta square. So, we are actually hypothesizing this form, okay, and this form, one way of thinking it is that yeah, it is quadratic in y, okay. Now, this is because in pi flow we know that it is quadratic, okay, so that's one of the reasons. If you look at y is equal to 0, what is u? U is 0, okay. If you look at y is equal to delta, what is u? U, okay. So, this profile essentially satisfies the boundary condition in the sense that this profile satisfies the fact that it's no slip at on the solid plate. It actually gets a velocity y. It could have gone linearly, it could have gone quadratically and so on. In fact, one would be able to, write down the full equation, you will be able to solve it, and when you solve it, you will find that the profile is very close to parabolic. In reality, the profile only deviates a little bit from parabolic, but we don't want to go through the entire calculation of doing it. So we are basically taking a simpler approach in which we are assuming that the velocity profile is parabolic.